This is a video on limits, and we are going to apply the squeeze theorem in each of these examples. Let's take a look at example 1. If 4x minus 9 is less than or equal to f of x, which is less than or equal to x squared minus 4x plus 7, for x greater than or equal to 0, find the limit as x goes to 4 of f of x. Now, we're going to apply the squeeze theorem. The limit as x goes to 4 of 4x minus 9 by direct substitution is equal to 4 times 4 minus 9. But that's equal to 16 minus 9, which is equal to 7. The limit as x goes to 4 of x squared minus 4x plus 7 is equal to, by, again, direct substitution, 4 squared minus 4 times 4 plus 7, which is equal to 16 minus 16 plus 7, which is equal to 7. So notice how these two numbers match. So by the squeeze theorem, we can say that the limit as x goes to 4 of f of x is equal to 7. Example 2. We're going to show that the limit as x approaches 0 of x to the 4th cosine of 2 over x is equal to 0. And what we want to do is we want to look at cosine of 2 over x. So we're going to focus on that piece of the limit first. When x is near 0, we know that cosine of 2 over x is less than or equal to 1 and greater than or equal to negative 1. Now, x to the 4th is greater than or equal to 0 for all x. And so what we're going to do is multiply through by x to the 4th. And when we do that, we get negative 1 x to the 4th is less than or equal to x to the 4th cosine of 2 over x, which is less than or equal to 1 x to the 4th. Now we get to start applying the squeeze theorem. So let's take a look at the limit as x goes to 0 of negative 1 x to the 4th. By direct substitution, that's equal to negative 1 times 0 to the 4th, which is equal to 0. And if we look at the limit as x goes to 0 of 1x to the 4th, we get 1 times 0 to the 4th, which is equal to 0. And notice how these two numbers match, right? They're the same. So by the squeeze theorem, we can say that the limit as x goes to 0 of x to the 4th cosine of 2 over x is equal to 0. And so that's how we show that that limit is 0. Let's take a look at example 3. Suppose f of x is less than or equal to x squared and greater than or equal to 2x minus 1 for x less than 3 and greater than 0. What we want to do is find the limit as x goes to 1 of f of x. Okay, another squeeze theorem example. So if we look at the limit as x approaches 1 of 2x minus 1, by direct substitution, this is equal to 2 times 1 minus 1, right? I just replace x with 1. And so this is 2 minus 1, which is equal to 1. The limit as x goes to 1 of x squared is equal to 1 squared, which is equal to 1. And so notice how these two values match, right? They're the same. So, therefore, by the squeeze theorem, we can say that the limit as x goes to 1 of f of x is also equal to 1. That's how we do example 3. And suppose we take a look at example 4. suppose I want to prove that the limit as x goes to 0 of x squared cosine of 1 over x squared is equal to 0. So start with cosine of 1 over x squared. When x is near 0, negative 1 is less than or equal to cosine of 1 over x squared, which is less than or equal to 1, right? The cosine is bounded between negative 1 and 1. Now, x squared is greater than or equal to 0 for all x. And so what I want to do is multiply through by x squared. And so therefore, negative 1x squared is less than or equal to x squared cosine of 1 over x squared, which is less than or equal to 1x squared. Now we're in perfect position to start applying the squeeze theorem. The limit as x goes to 0 of negative 1x squared is equal to, by direct substitution, negative 1 times 0 squared, which is equal to 0. The limit as x goes to 0 of 1x squared is equal to 1 times 0 squared, which is also 0. So notice how these are the same value, right? So by the squeeze theorem, we can say that the limit as x goes to 0 of x squared cosine of 1 over x squared is also equal to 0. And that'll conclude this video where we did 4 examples applying the squeeze theorem in the section on limits in a Calculus 1 class. Okay, thank you.